Okay, so question 17, okay. P of n is equal to 9 by 4 to the power 2n minus 5n to the minus 1. Now, what happens this time is we're going to test part 1. It's going to be test for P of 1. So when we test P of 1, what we're going to get is 9 times 4 squared, 2 times 1, 4 squared, minus 5 times 1 minus 1, 1 minus 1 being 5 to the power 0. And what we're going to have here is 9 times 16. So 9 multiplied with 16 is going to be 144. And minus 1 is 143. And this 143 divided by 11, because we have to see if it's divisible by 11, divided by 11 equals 13. Okay, so true for P of 1. So it is divisible for P of 1. Now part 2, we're going to assume true for P of k. Now when we assume true for P of k is 9 by 4 to the power 2k minus 5 into k minus 1. Now step 3 is to test for P of k plus 1. Now P of k plus 1 has the following parts. P into k plus 1 equals 9 into, now 2 multiplied by k plus 1. It's going to be 4 times 2k plus 2, close bracket, minus 5 times k plus 1 minus 1. Now, what we're going to have here is we're going to separate out, so it's going to be 9 multiplied by, now separate out 2k plus 2, you're going to get 4 squared and then 4 to the power of 2k. We also want to separate out k minus 1, so k minus 1 is here and here, so it's going to be minus 5 to the power 1 to the power of 5k minus 1. And we put this in, 9 times 4 squared is 144, 4 to the power 2k minus 5 times 5 to the power k minus 1. Now, we have 5 times the amount of P of k. So, if I was to multiply, see the way it's 5 to k minus 1. If I was to multiply P of k by 5, what I'd get is 45, 4 to the 2k, and I'd get minus 5 times 5k minus 1. So what I can do here is, knowing this, I'm going to separate out the 144. I'm going to break it up into 45 to the 2k. And I'm also going to break it into 99, because that's the remainder left, 4 to the power 2k. Now, what happens next is it's going to be minus 5 times 5k minus 1. Now I'm going to factorize this part and turn it into P of k, because this part here is basically 5p of k. So what I'm going to do is factorize out 5. It's going to be 5 into 4 to the power 2k minus 5 into k minus 1, close brackets, and that's going to be 99, 4 to the 2k at the front. So that's P of k plus 1. Now, what we have here is this part here is divisible by 11. 99 divided by 11 equals 9. Okay, and then this part here is assumed divisible by P of k. So, therefore, hence P of k plus 1 is true if P of k is true. Hence, by the principle of mathematical induction, P of n is divisible by 11 for all values of n elements capital numbers n. Okay, so the next one here is P of n equals 8 to the 2n minus 3 to the 2n. Question 1 is asking you to evaluate P1 and P2. Well, P1 is going to be 8 squared minus 3 squared, which ends up to be 55. P2 is going to be replace n with 2, and it's going to be 8 4 minus 3 4, which equals 4015. Okay, now part 2. Express P of n plus 1 in the form a into 8 to the power 2n minus b by 3 to the power 2n. So P to the power of n plus 1 ends up to be replace, so it's going to be 8. Now 2 times n plus 1 is going to be 2n plus 2 minus 3 times 2n plus 2. Separate out the powers and we're going to get 8 squared, and then we're going to get 3 squared, and then we're still going to have 8 to the 2n and 3 to the 2n. And once we've done that, what happens next is 64 by 8 to the 2n minus 9 by 3 to the 2n. And then, so that's our answer for that one, 64 and 9. Now, for part 3, what I want to show is, show that P of n plus 1 minus 9P of n is 55 by 8 to the 2n. Okay, so, part 3, P of n plus 1 minus 9P of n. So, what we're going to get here is 64 8 to the 2n minus 9 to the power of 3 to the 2n minus 9 times 8 to the 2n minus 3 to the 2n. That's going to be minus 9 times 8 to the 2n plus 9 times 3 to the 2n. The 9's cancel out. And then we're going to get 64 minus 9. 64 minus 9 is 55, 8 to the 2n. Okay, last part. Hence or otherwise show that 5 is a factor of P of n for all n element n. Okay, so this is our principle of mathematical induction. We say that P of n equals 8 to the 2n minus 3 to the 2n. Step 1, test P of 1. So when we test P1, we're going to get 8 squared minus 3 squared, which is 55. 55 divided by 5 equals 11. Hence, true for P of 1. Now step 2 is assume true for P of k. Assume true for P of k. So P of k therefore is 8 to the 2k minus 3 to the 2k. Now part 3, prove for p of k plus 1. Okay, so prove for p of k plus 1. So we're going to get p of k plus 1 ends up to be, now replace k with k plus 1, so it's 2 times k plus 1, so it's going to be 8 to the power of 2k plus 2 minus 3 to the power of 2k plus 2. What we're going to get here is 8 squared by 8 to the 2k minus 3 squared by 3 to the 2k. Then what we're going to get is 64, 8 to the 2k minus 9 by 3 to the power of 2k. Now, what we have this time is we're looking at the two of these, and we can see that we need to make p of k out of this. So I currently have 9 times the amount of p of k. So if I said 9 p of k, 9 times p of k is equal to 9 times 8 to the 2k minus 9 times 3 to the 2k. So that's 9 times p of k. So I have this part, but I need the other part. So I'm going to say is 9 by 8 to the 2k minus 9 by 3 to the 2k. Now, I've taken 9 out of the 64, so that leaves 55 8 to the 2k over. Now, when I break this up into two parts, so it's going to be 55 by 8 to the 2k. I'm going to factorise out the 9. And then inside the 9, we're going to have 8 to the 2k minus 3 to the 2k. This part here is divisible by, assumed divisible by 5 by p of k. So it's assumed divisible by 5. Okay, and this one here is divisible by 5, and 55 divided by 5 equals 11, and that's still p of k plus 1. So, therefore, hence p of k plus 1 is true if p of k is true. Hence, by the principle of mathematical induction, P of n is divisible by n, is divisible by 5 for all values of n that are natural numbers. Okay, that's that part done.